We are very happy to have Vinny here today. Vinny has been doing his PhD in Zurich and came to Berkeley like 3 years ago, and is now a third-year postdoc up at the lab, working with Ben Nachman, who many of you also know. Vinny's working among others, at experiments at the Large Hadron Collider, today he's going to tell us about how you can accelerate the discoveries in high energy physics using AI, presenting all different kinds of methods. So when you're ready.
Yeah, thanks a lot. Thanks for the introduction. I'm very glad to be here, and glad that everyone's here, even though there was a tsunami alert. But it tells how motivated people are. I think to start the talk, I want to introduce a little bit my field. So working in particle physics and collider physics in particular, which is a bit different than what you might be most familiar with. And in its core, particle physics is basically the human endeavor to understand what the universe is made of. And this question of what the universe is made of has been asked for centuries now, and people are trying their best to try to figure out an answer. But more recently, we were able to do more progress along trying to answer this question. We put all the elements that we knew about in a periodic table, tried to organize the things that we would understand. But even later, we understood that even the things that we thought were very different, an atom of hydrogen compared to an atom of iron, or an atom of oxygen, things that we are eating, things that the chair that you're sitting down, even though they're made of very different components, in its core, they're made of the same stuff. They're made of protons, electrons, and neutrons. And even protons, we learned that they are not very fundamental. They still have stuff inside. They have something that we call quarks. And so far, we believe quarks are fundamental. It might not be, and might have new discoveries in the future. But the way that we are able to identify these discoveries was through particle colliders. We basically smash particles together and see what comes out of these particle interactions. Because one of the most famous equations in physics, E equals mc squared, means that energy can create mass. So if you accelerate these particles to speeds near the speed of light, put a lot of energy into that, we can create new particles out of these particle interactions. And from these interactions, we can study how the universe works. That means that we need a very big experiment, and in particular, the Large Hadron Collider accelerates particles in this 3-mile ring. Where just to give a reference on how big that is, you have this map here on the right, where the center is here, is Berkeley. And you can see like it goes to the west mostly, outside the marina already. At north, you go to Alcedo, Emeryville in the south, and so on. So these experiments is pretty big, and one of the biggest experiments that any human would be able to build in the history of humankind.
It's just that it's canceled.
It's not canceled, what do you mean?
Europe, no, the tsunami.
Ah, it's not canceled,
yeah,
yes. But yes.
I know what you're saying,
This is about a tsunami network.
No, the Large Hadron Collider is
But
not
I can't
canceled.
do
That'd be sad.
But what I want to talk about today are the challenges that we still face in this field. Because even though we have a lot of data, we understood a lot of things about the universe in the past 10 years or so, we still have a few challenges that we still need to address. And these challenges, they can hopefully be solved also using machine learning and AI. So we start from the computing challenge. Because I mentioned that just through particle interactions, you can create new particles, which is great. But there's a caveat. Depends on the particles that you want to study. The likelihood of producing them through particle collisions is not the same. Which means that if you want to create some very specific set of particles, you see in this x-axis, the likelihood of them happening through a particle interaction can vary drastically in orders of magnitude. And if you're interested in the most rare processes, they can be 10 orders of magnitude lower than the most common outcomes of particle interactions. And that means that we need a lot of data just to be able to have a chance of producing any of these most rare physics processes. So let me give you an example. We discovered the Higgs boson, the last missing piece of the model of particle interactions that we have right now, about 10 years ago. And even though the theory describing the Higgs boson has been around for more than 50 years. And the reason why it took us so long is because the chances of producing a Higgs boson through particle interactions at the LHC is around 1 in 10 billion. This number is incredibly small. And just to give a reference again, the odds of being struck by lightning is 1 in 15,000. Or being killed by a vending machine is 1 in 112 million. And winning the Powerball, winning the lottery, is 1 in 300. So just being able to produce 2 Higgs bosons is already less likely than you being struck by lightning, winning the Powerball, and then being killed by a vending machine. Which means that this plot here on the left, it shows the discovery of the Higgs boson, where we saw an excess of events on top of what we expected to be the background. Had a handful of events that we recorded, and this handful of events require a lot of particle interactions to be able to be collected. And the trick is that right now, we can amass a lot of particle interactions in a very short amount of time. For instance, we can do 600 million collisions per second, and we can use the data for analysis of what is coming out of these particle interactions. But as we move towards the future, the plan is to upgrade the NHC experiments to have even more collisions per unit of time, because then it's more data, more data in the same amount of time, more likely for us to be able to produce even more rare stuff. But also means that the computational power that we need in order to be able to keep up, not only with the data that we are collecting, but also with simulations that are necessary to compare or theory predictions with the measurements, also need to be scaled up. And if we keep just our own workflows that we have right now, which are already very optimized, we can already see that they go very above the expected amount of budget that we foresee for the future. And asking for more budget is always hard, which means that we have to do something about the computational complexity of these particle interactions.
Why is there a big jump in the middle there?
Yeah, because in 2029 is when we are going to do the upgrade.
Oh,
So far is current status until 2029. After that is when you ramp up and increase that amount of interactions. But where does the computational bottleneck even comes from in the first place? And I think here is interesting to look at how we do normally our own analysis of the LHC, where we have our particle interactions that we record with our own detectors. And from these detector measurements, we can measure our data, calculate some physics observables, and have some estimates of what nature is telling us. But that is not enough. We need to have an estimate of what our current theories tells us about particle interactions. And that means that first we need to have the simulation of our physics theories. So starting from Lagrangians and getting particles that are produced to particle interactions. Then we need to simulate the detector response, which is very computationally intensive. And from that, we can do the same procedure that we do with our real data from particle interactions and do this comparison between the two. If they are in agreement, that means that our theory is doing really well. If they are not, then we have something to learn. But the detector response is the part that is most expensive to run, mostly because our detectors, they have millions of components to be able to perform very precise measurements. And simulating these millions of components can be very intensive. And that was one of the main motivations of trying to replace that part of the detector response using some AI method. And in particular, generative algorithms can be very useful for that. Because a generative algorithm, in a broadly speaking way, is any algorithm that takes some very easy to sample noise, so let's say a Gaussian noise that can quickly produce a lot, and convert that noise into something useful, which could be a picture of a dog, or it could be just the response of my detector. But there is one specific kind of algorithm that I want to talk about today that has been very useful for both in physics, but everywhere else. And those are diffusion generative models. For instance, I made this illustration, which is not hard at all. You're sending a prompt to ChatGPT, where you generate a picture based on some specific sentence or some specific condition. In this case, our scientists here did math, working on science and machine learning, and you see this very cool picture on the left. Kind of realistic, kind of not, of course. You see the Berkeley Tower, you see some very nice backgrounds. You see a car here, which I don't know what is related to the prompt. But you see that, at least visually, it looks pretty nice. But you can use the same kind of technology to say, give me a response of my detector, given that the condition is an electron that is passing through. And the idea of these diffusion models on how they work and how they are trained is actually very tied to physics and to things that you might have studied before at university. For example, the name diffusion already tells you a lot about the process that these algorithms they use to learn how to generate these images. Because first, you have this stochastic differential equation. So Brownian motion, you should be also familiar with if you study those things. But the idea is that I can start from my data, time equals 0, and start applying perturbations. So imagine that I'm applying perturbations over time, Gaussian perturbations, such that after very long periods of time, my whole data becomes Gaussian noise. And this equation here is fully specified. You have these drift and diffusion coefficients. You basically choose those parameters, and you can run your diffusion forward. There's nothing to learn here. But of course, that's not so exciting, right? If I take any data and I perturb with a Gaussian, I get a Gaussian again. That's not very exciting. The exciting part is to go backwards. It's do a denoising process where I can start from the Gaussian and then get to something useful, get something like the simulations that I want to perform. If you want to do the opposite, that means that I need to solve the reverse stochastic differential equation, which is very similar to the forward one. You still have the same terms, but you have this additional term here, which is the gradient of the log probability of your data. And this term is also known as the score function. Well, normally that's not something that you can get from the data itself. If the data is high-dimensional, the probability is intractable. The gradient is also not going to be easy to estimate. But you can do something that is called score matching, which I can go in more detail if you're interested. But I think it's also interesting to just show that it actually works. You can train these algorithms. They are very easy to train. And all you can do is that you can give examples of your real physics simulation, train these algorithms with those examples, and generate new particle interactions from the specific type of particle that you want to simulate. And the results, they look very nice and very similar to what you actually have in your full physics simulation. And they scale to very large amounts of detector components. So this was the first diffusion model in high-energy physics, Kali score, and also the first simulation that we went up to 50,000 detector components. But then there was an issue when we were evaluating this model, because looking at images is always nice. But you also need to look at some other distributions that want to be sure that we get it correctly. One of them is the amounts of energy that is deposited in each layer of your detector. And in the beginning, what we got was this distribution here on the left, where the diffusion model in green looks reasonably okay compared to the full simulation, that is the dotted lines, even better than other attempts that we try with GANs and other generative models. But it's still not yet there, because that information here is very crucial to us to get correctly, because that can give us not only the estimate of the energy of the particle that's passing through, but it's also used to identify what is this particle and to separate, for example, an electron from another species of particle. So what we did in a follow-up work was to, well, if I'm already estimating the score function of my data, then maybe I can break that down to two components. One that only focus on this distribution here, because that one is very important, and use that information to condition the other score function. And when we do that, we do get these improvements where now the distributions that we generate, they look way nicer and closer to what we expect. And the main advantage, of course, is not only that we can get something that looks very realistic, but it's orders of time faster, almost 1 million times faster than the full simulation. Of course.
What is it conditioned on?
Yeah, in this case, condition on the particle that's passing through and the energy of this particle. And right now, we are working on trying to move these kind of algorithms to the Large Hadron Collider, to real experiments, where we can replace this full simulation of the detector through a surrogate model, through a generative model that can do that, but much faster. Now let's talk about a different challenge, a measurement challenge. Well, first let's talk about detector simulation, but I want to talk about something that is connected to that, but a bit before that. Because normally, the only way they have access to physics is through what our detector is going to tell us. So our detector measures. But the things that we actually want to understand about the particle interactions, they happen before the detector interactions. But the detector will distort these measurements. They will distort the observations that we do because the detector is just not perfect. So there would be, if there was a way that we can undo the detector effects, at least in a statistical way, and correct our observables to how they look like before the detector interactions, then that would make the comparisons with different theories way easier to perform. And that's what unfolding basically means. Where in the way that we normally do that in high-energy physics is through histograms. We first measure some physics observable and use the response of our detector to create these histograms. And then we apply a statistical procedure to correct these histograms to get this distribution on the right, which is again another histogram, but now corrected for the detector effects. And that's how we publish our data. That's how we publish our results. But the issue is that if we always need to put things on a histogram to be able to perform these detector correction, then if you want to measure something that is not very amenable to a histogram representation, then we are in trouble. And that's also one of the reasons why a lot of work that we had even in 1978, for example, so many years ago, has been ignored by the experimental community because they would try to introduce new observables, where these new observables, they were not really just counts of something that you can easily put in a histogram. They could be 2-point correlations between distributions, which is something that is very common to measure in cosmology, for example. But in high-energy physics, you normally don't do that, just because of this issue of not being able to correct these things in a way that is easy to do using our histogram. And just to show here, this idea that was first shown in 1978 had the first results of what they were proposing published in 2024, so this year, with histograms itself. So that was basically the time it took for them to figure out how to put that in a histogram and do the corrections. But there is a way that we can use machine learning instead to do these corrections that don't require any histograms or anything. And it's even nicer because we can use any physics observable and in principle even encode the full particle interaction and correct everything simultaneously, which means that any observable that you want to calculate afterwards will already be corrected. And this idea was introduced by Ben a few years ago. That's called omnifold. Where the idea is somehow pretty simple. You take your data, you take your simulations, and you want to reweight your simulations in a high-dimensional space to look like your data. And after you get this reweighting performed, then now you have the simulation corrected for the response of the data that you want to match. But the challenge here was, well, if I have a very high dimensionality, if I have very high dimensions on number of particles and number of features that I want to include, how do I calculate some reweighting function in this high dimensional space? And the trick is that if you just train classifiers, they are basically learning a reweighting function. Because classifiers, they approximate a likelihood ratio between your two data sets that you're trying to distinguish with. And it turns out that the reweighting function that you need to apply to your data is the likelihood ratio of the two data sets. So using these insights of, well, if I just train a classifier between my data and my simulation, then I can set up an algorithm that can do this correction for me. And that's the algorithm that we use, for example.
What do you mean by classifier between data and simulation? Like what's it classifying?
Data and simulation.
Oh, between if it's generated by simulation or generated by data. Okay.
Exactly. And that's exactly what we use for these measurements that was published 1 year ago. They use the data from the H1 collaboration, where they have an electron colliding with a proton, where these particle interactions get interesting because basically the electron can only interact with a proton through the electromagnetic force, or through an interaction that has a gamma or a photon involved. And most of the time, what happens is that if that photon is very energetic, it just kicks a quark out of the proton, and the proton is positive. So that means that more likely the charge of the particle that's being knocked out is going to be positive. And that's exactly what I see in these plots on the left, where if you start from lower energies and keep increasing the energy, the charge of the objects that are going to be kicked out, they get more and more positive. Where in the case of low energies, there's some other stuff that happens, but at higher energies, you get this expected behavior. But we can also quantify the same information by calculating what is the mean value of that charge as a function of the energy. And I can put this in a plot in a way that is very easy to compare with different theories and fix some of the details of the theory that we can tune. But also, we don't need histograms to begin with. Because again, we can just calculate the average of something just taking our data set. And that's very useful because normally, if you had to do it in the standard way, that means that for each of these licensing energy, we have to create a histogram and take the average of the histogram. And that also means that you need to be very careful how we define the binning of this histogram, because you don't want the binning to interfere with your estimation of the mean value of the data. But here, you don't have to care about any of these issues, since you can bypass the histograms altogether.
So all of these points are weighted towards the
Exactly.
data or the, okay.
Exactly. So the third challenge that I want to talk about is on the discovery challenge. And one of the main issues why we still smash things together is because you are interested in understanding if there are things that go beyond the theory of particle interactions that we have right now. And in particular, we know that we have things that we don't understand. We know that dark matter is out there from cosmological probes, but we don't know what it's made of. But there are also some additional questions, why there's more matter than antimatter, where these things are coming from, and what can be the cause for them to exist. Maybe there is a dark matter particle that we can produce at the LHC, and we can measure. If you don't know what you're looking for, then that makes it for a hard challenge. So I'll give you an easier challenge. So if I ask you, how do you find a needle in a haystack? The answer is pretty simple. Use a magnet. You just go there and you can quickly find if there is a needle over it. And that's normally how we do it at the LHC as an analogy. But normally we start from the magnets and we hope there is a needle in our data. So we start from a specific theory that can be well motivated and predict something that we can measure. Then with that theory, we go to our data and search for it. If you find a needle, then that's great. That means that we get a Nobel Prize because now we have a new theory and everything's shiny. If we don't, that's still okay. That means that, well, that needle is not the one that we are looking for. But the issue is that we've been using magnets and different types of magnets too much, I would say. Each line of this plot here shows basically one different theory that we search for. We didn't find anything. And we can then put bounds on the parameters of this theory and say, well, if this theory is still correct, then at least these particles cannot be there. And that means that for each line corresponding to one analysis at the HC, probably 3-4 years of the student life of a PhD students. And in the past 10 years, we've done lots of those and hundreds of these measurements, even though we haven't found anything yet. But maybe there is some other direction that we can take that is complementary to the strategy, where we don't even think about having magnets in the first place. But our question is, what is not a hay in a haystack? Because at least the haystack we understand. The standard model of particle interactions we have a good understanding of. So let's try to look for anomalies. Let's try to look for things that are not very compatible with the theory that we have available. Because if you do find something exciting, cool, we found something exciting. It's already better than the past 10 years. And we can try to interpret what we actually found. If it don't, then it might be sensitive to many different types of theories that someone in the future might propose, and they can already infer if their theory is viable or not. And one way that we can search for anomalies is through autoencoders. So an autoencoder is an ML algorithm that you take your data in some high dimensional space, you compress it to a low dimensional space, and then you decompress it back again. And what you're trying to optimize is to minimize the difference between your inputs and the decompressed outputs. And why this algorithm works for anomaly detection is that you can imagine that for things that are very common in your data, the algorithm will learn to do that very well, the compression and decompression. So the error of the reconstruction will be very small. But if I give you something completely off, something that has never been seen or not very frequently in the data that you have available, the reconstruction of my autoencoder won't be as good. And the reconstruction itself can be used as an anomaly score that we can attach to your particle interactions. But why stop at one autoencoder? We have two of them. and make them decorrelate in a way that each of them can tell me what is the reconstruction error that I see in my particle interactions, in a way that the orange lines that corresponds to the background or just the standard theory, they have low reconstruction error, and they are basically decorrelated with each other. But the signal that I care about is not going to be decorrelated, and it's going to have higher reconstruction. Because if I can have these two X's, then I can use something in high-energy physics that we've been using for a few decades now. That's called the ABCD method. But the idea is very simple. If you want to estimate what is the number of false positives that you have in your data, you can take these two observables that you created, my two autoencoders, and break their 2D region into 4 spaces, where the region where both anomaly detection algorithms are telling that are anomalous are going to be my region of interest, the region where I want to estimate the number of false positives. And to do that, I just need to use the number of observations that I have in the other 3 areas and get this very simple ratio. So if a simple trick, we can get the number of background events in the region that I care about, the region that I have anomalies. And that actually really works well. So in this plot, what I'm showing is the false positive rate in the x-axis and the significance of my data, which means that I have an estimate of my background, I have my data. If I have an excess, then this excess is the number that I'm going to use to calculate the significance. And there are 2 important things here. One is the blue line, where I don't inject anything, I only have background. If I don't have anything new, then data and estimated number of background events, they match each other. Significance is below 1. So that works. But if I inject something, just 0.1% of my data set is going to be some new physics signal, which could come from very different theories, having very different particles produced. 99.9% of everything is still background. We still see that the significance for each of them increases and can be even up to 4 sigma, which would be very close already at discovery, even if the initial significance was very small. So before I go to the end of this talk, yes, I still have a few minutes, I want to talk about something that is slightly different. There's only foundational models. And I guess the word foundational model is a bit of a buzzword nowadays. So we've been hearing a lot about that from ChatGPT and from models like that, where ChatGPT can tell you how to fix your code or tell you where to go for dinner and do a number of different tasks that they were not necessarily trained for. And that kind of new technology that's been around everywhere nowadays is something that maybe you can try to take inspiration from and use for scientific applications. But how does a scientific foundational model would look like in the first place is not very obvious, or what kind of things they're going to accomplish with this model is also not very obvious. But one way that I think it's easy to break down this question is by trying to address 3 different points. So the first one you need to address is what kind of data that you want to give to the model, where the model is going to ingest this data, and the learning procedure that we are going to tell the model to do is going to dictate what the model is going to learn from the data. And that tells you what the model is going to understand from the data that you're giving to the model. So in the case, for example, of ChatGPT, my inputs, they are tokenized versions of language. I just give letters or words as my inputs. I use a big transformer as my model. And I can have these different learning tasks, for example, one that I can mask words in my sentence and ask for ChatGPT to predict which are the ones that I masked, or just complete my sentence and write, for example, 1, 2, and have different predictions of what should come next, like 3, and some other words like this. But for particle physics and quantum physics particularly, what we would like to do is have our data to be exactly the data that we measure, our particle interactions. So you have particles with some specific features. The model that I want to talk a little bit about it is going to be a combination of a transformer, since those scale really nicely for large amounts of data that we have in the DTC. But we can also combine that with graph neural networks, it can give more information about locality of my particle interactions. And the learning scheme that we're going to use is going to be a mixture of asking my model to identify different particles of my simulation. So try to classify different particle interactions for each other, but also trying to generate those, try to generate new particle interactions. And it turns out that training a model like this and then fine-tuning for different tasks works really well, both in terms of how fast they converge to different tasks that you want to use and different data sets that was not used during this pre-training process. But for example, it also improves a lot of the metrics from benchmarks that we had in the past. For generative models that I was talking at the beginning of this talk, we evaluated on different data sets. The benchmark that I'm showing here and the value of these metrics, they're not so relevant, but the important thing is that only learn, which is the model that we're introducing, improves all of them compared to different models that we had in the past. For unfolding, we can do the same thing and apply to an unfolding task in a different data set. Just do the fine tuning, and we also see the anomaly is more precise at determining the unfolding. And for anomaly detection, we can take the same model again, apply it to a different task that is to try to find new particles. And all you observe is that we can improve the sensitivity to new particle interactions by using 4 times less data, which is very important as we move towards the future and try to double the amount of data that we have collected becomes harder and takes years. In the paper that I can also send you if you're interested, we also have a number of other benchmarks. And in every case, either OmniLearn becomes better than previous benchmarks or converges much quicker, which is nice because that means that all the work that I've done before has been superseded now, but I'm happy because at least it's by something that works nicely for all these different tasks at the same time. But we can also try to think about the future. And what do we want to...
What do you mean that you have a thing that does all the tasks? It's just like a same generative framework conditioned on different things for producing research results, or?
Yeah, exactly. So imagine that I want to just train an additional classifier. Then I just need to replace a few layers of my network, just like the last one, and then fine-tune these data sets. And for the future, maybe you can try to think about having different types of physics or even beyond physics within these models. Maybe you can try to combine the data from the LHC, where we have a lot of simulations, we have a lot of data available, and pre-train models that can maybe be used for some other applications. For example, cosmology or maybe some chemistry applications. And that's not exactly far-fetched, since the data from the LHC is basically a point cloud. You have a set of particles that have each of them some additional features. But this framework, this structure of data sets is also very common for cosmology. You can just model the stars in the sky as a point cloud if you want, or maybe some galaxies, depends on the data set that you use. Or you can model each point in your point cloud as an atom, and you have the chemical bonds between them. So of course the tasks are changing, but the structure of the general data set is not so different. But that does not mean that it's very obvious what kind of model you should be using for that, nor the learning tasks that you should be asking the model to accomplish. But I think it's just interesting to start thinking about these things, because that's already the conclusion of this talk. For the Heinrich physics folks, AI is being used for a few decades now, and the usefulness of AI is growing the more the data that we collect. We have now these more general models that can be used for a number of different tasks, where the idea is that why start training something from scratch if we can have a model that can do better just by doing the fine-tuning in the first place. But in the same way that more and more scientists are becoming interdisciplinary, they're interested in other fields of science, and hopefully why some of you are here today listening to a particle physics talk. We can also try to think not only of interdisciplinary scientists, but interdisciplinary models. Models that maybe can also have some understanding or some commonality with other fields of science in the same way that I can barely talk about astro applications, and use that knowledge to get something exciting, something that can maybe connect different problems, where dark matter could be discovered through a combination of particle physics and cosmology. And that's the end of my talk. And let me know if you have questions.
Thank you very much for the very nice and very comprehensive talk. I'm sure there are questions.
So most generative models are stochastic, right? So for the same problem,
Yes.
get different. I suppose that's not something you want in your model. So how do you deal with that problem?
Yeah, for detector simulation, we actually want that property because if I have the same electron, the same energy, the detector response that this electron will generate is not going to be deterministic because there is a probability of this electron interacting with my detector material, which means that the same particle, same energy can give me very different interactions. And in this case, we really want this stochastic property. And that stochasticity is well represented by the Johnson model. So it also gets the same distributions, which is also nice.
Yeah, I have a similar question. So basically, generating model is to propose new candidates or new possible physics or materials in scientific discovery. I was curious, in high energy physics, how can you validate the stuff you generate? This is always needs to come to by experiments or validation.
Yeah, definitely. Yeah, we definitely have to validate. And even the physics simulators that we have to validate because we have data. So we have some standard candles or processes that we understand well, what is the signature, that we can then compare with our simulations, they come from the physics simulator or from the machine learning method that we can use not only to validate the simulation itself, but to calibrate the simulation. There might be some observables that we care about, where the data we know what they should look like, and we can use that to calibrate these simulations.
How large is the gap? Basically, how expensive for one validation?
No, it's not that expensive because the validation is not per particle interaction, it's per distribution, which means it's already the average of a number of particle interactions and how do they look.
So what's the current progress for Atlas or CMS in accepting those fancy technologies? I think you show some analysis using omnifold or anomaly detection. What about the fast simulation?
Yeah, for the test simulation, right now, Atlas already uses a generative model to replace the calorimeter index. So that's the Pascalogan, if I'm not mistaken the name, but it's made, well, as the name suggests, it's based on a GAN. So they're already very receptive to using these different technologies. And it took a while for them to be able to put that in their own pipeline and the workflow and make them work nicely with the rest of the workflow that they need to run. So it took a bit longer for that to happen. But right now, hopefully, it's a lot easier, which means that as long as you have a new model, you can basically replace what they have, put your new model there and see what happens. Of course, it should need to do the calibration and so on and so forth. Well, it should be a lot easier to do. And CMS is also doing the same, but they are not.
Yeah, so when you're reweighting the simulation data to match the experimental data, is that really the only way of doing that? That we don't just understand that where the simulation and the experiments differ enough to actually correct it without like machine learning? It seems like maybe giving up a little bit on that problem. Yeah.
Yeah, and you can also use generative models for that, but I guess the question is more interesting as to if you have more control about the things that you're doing. Because for unfolding in particular, even though we don't know exactly what we are correcting, just putting weights on the simulation, the point is that we can use that to compare the different theory predictions and know what are the difference between the two. So in principle, I could also take my theory, pass through my detector simulation, and do the same comparison. You know, the detector simulation, as I mentioned before, is very expensive. So if a theorist has a new theory, and they go to the experiment and say, oh, can you run this? Maybe someone will do it. It might take a while. But it's much easier if I give you a data set after the reweighting, where you don't know exactly what was reweighted, but you know that this data set is representative of your data.
Yeah.
And you as a theorist can take your theory and try to figure out what is the difference.
But there are ways to exactly match the detector without machine learning, though. It's just that this is faster.
Yeah, exactly. You can run the detector simulation, that's fine. But then it's the reconstruction parts of how the detector images or the detector response comes into particles and so on and so forth.
So what would be the inputs to the foundation model that does multiple tests, such as cosmology and hydrogen physics? For cosmology, you have properties of stars. And for hydrogen physics, you have properties of particles. So how would you represent the data in a generic way that can be fed into the model? It is a meaningful answer. There is some text descriptions or whatever.
Yeah, that's a great question. And text is definitely something that can be used. I just don't like it so much trying to tokenize your data because normally our distributions they are continuous. So if you tokenize them, you lose a little bit of information on that. But that's definitely possible because then you have the same tokenization for every different data set. So that's one way to do that. But at least for cosmology and for some chemistry applications and energy physics, just the geometrical location of these particles can already be used and also translated to other data set. For example, if I have particles in a jet, I can use the delta R, delta eta, delta phi for my particles. If they are in the sky, I can use just the coordinates with respect to either the galaxy plane or to the local coordinates of the sky. Or if I have atoms, I just look the local coordinates of these atoms.
How do you tell the model that it is a star or particle or whatever?
I don't know. So that's the question that hopefully we can address together.
And
But yeah,
how can you encode uncertainty information in those things as well?
yeah, and depends what you mean by uncertainty.
Like the position, geometry, those are not exactly
Right.
deterministic.
Yeah, because there are many types of uncertainties that we need to consider for anything that we do. For instance, if you care about the statistical uncertainty in our labs, you can do SBI. You can do things that we can use the simulations that already give us some decent understanding of other things that we're giving in, and use that to see how certain my network is going to be on the prediction of something. If you're talking about systematic uncertainty, so I know that my detector is not perfect, but I know where in my detector is not perfect. Then including those things can be a bit trickier for these standard methods. You can still do SBI and need to condition your model on these kind of variations of your detector response. But in principle, there's nothing special about foundation models in this case that does not translate to standard ways of we do our own analysis.
Is there any working foundation model that does multiple tasks in different disciplines at the same time?
Not that I'm aware of. But if you, yes, we could be the first.
All right. If there are no more questions, we wish to thank Vinny again for a nice talk. And if I'm not mistaken,